Greetings, welcome to section 3.4, rational functions. Thank you for watching this video. I really appreciate that. Okay, in the last few sections we built polynomials based on positive whole number power functions. In this section we're going to explore functions based on power functions with negative integer powers. These are called rational functions. So quick review, what does x to the negative n mean? Well, hopefully someplace in the dark, deep, dank recesses of your brain you remember that x to the negative n means 1 over x to the n. And that's like the most basic rational function you can have, where you have 1 over x raised to a power. So let's start with the most basic of the basic, and let's let n be equal to 1. Let's go take a look at one of our toolkit functions. In particular, let's look at 1 over x. So f of x is equal to 1 over x. Now, you hopefully remember from our previous work with this what the domain and the range of this function is. So if you think about the domain, and we do that in set builder notation, it is a set of x's such that x is not equal to 0. Now, why do we know that? Well, because you can't divide by 0. You put a 0 in here in this denominator, you're going to get division by 0. That's bad. What about the range? Well, the range, the long run behavior of this function is that as x goes to positive infinity, so in other words, as x heads out to positive infinity, we see that the y's are coming down and y is approaching 0, isn't it? Same song, second verse in the other direction. As x goes to negative infinity, we see again y is coming down, or in this case coming up, excuse me, and it's also coming up towards 0. So what that means is that y is not equal to 0. All right, so that should look familiar. That should be a kind of review from our previous work on domain and range of this function. Let's talk about the overall properties of this, okay? So f of x equal to 1 over x, we just said what the domain and the range is. The short run behavior, what that means is we're talking about what's happening around the origin. And as we're coming around the origin, let's back up to the graph here for just a minute. As we come in towards the origin from the positive side, so in other words, x approaches 0 from the positive side, we see we're blowing off so that f of x is going to infinity. And as we come to 0 from the negative side with respect to x, what we see again is that f of x is blowing off to infinity, but this time to negative infinity. All right, and so what happens there is that since x is not equal to 0, we have a line of demarcation that you cannot pass through. That line is referred to as a vertical asymptote. That is, if I came in here and drew that in my graph, this vertical line right here, this axis, this y-axis is a vertical asymptote. Go back to the pen here. That would have been a better tool to stay with in the first place. Okay, so we have a vertical asymptote at x equals to 0. Whereas that's the vertical line, x equals to 0. So back here, that's exactly what we're saying, is that x equals to 0, that equation of that line is a vertical asymptote. All right, same song, second verse with respect to what's going on with the x-axis. So if we look at the x-axis here, I put in this dashed line, the x-axis is playing starring role of a horizontal asymptote. So y equals to 0 is the equation of the x-axis, and that is what's referred to as a horizontal asymptote. Okay, what the heck are asymptotes anyway? We should probably take a moment and define those a little better. So vertical and horizontal asymptotes. A vertical asymptote of a graph is a vertical line x equals to a. Get the pen back to the right color here. Where the graph tends towards positive, negative infinity as the inputs approach a. So in our case that we just did a minute ago, notice we had what? X was approaching 0 from both the positive and the negative side. And in both cases, we blew off f of x either to positive infinity or negative infinity. So if that's the behavior of the function around that point a, where x equals to a, then you have a vertical asymptote. All right, now reverse that idea. So this time, let x go to either positive or negative infinity. And if f of x goes to a fixed value, then in that case, y equals to b is going to be the equation of that horizontal asymptote. Keep in mind that these are both equations of lines. That's the equation of the vertical line, x equals to a, and that's the equation of the horizontal line, y equals to b. Okay, cool beans. All right, so let's do your turn pi here. So let f of x equal to 1 over x. find g of x, such as a transformation of f of x given by g of x is equal to f of x plus 2 plus 3. Okay, so let me get up a whiteboard here for us. All right, so what do we got here? So we know that f of x is equal to 1 over x, and our g of x function, let's see, what is our g of x function equal to again? It's f of x plus 2 plus 3. So that's equal to f of x plus 2 plus 3. All right, cool beans. Now, what do they want from us? Well, they want us to give a sketch of that function. So let's come in and let's make ourselves a glorious coordinate system here. So there's my x and my y axes. And so we know that f of x equals to 1 over x. That's our stock function. We know that in that case, let me just lightly put it in here in red. We know that it would look something like this, right? Let me get a little more down here with that, okay? And so what we know is that our vertical and our horizontal asymptotes in that case were the axes, weren't they? Okay, so what do we know about f? What happened to f? Well, f got transformed by getting shifted 2 units to the left and 3 units up, right? So what that means is that our asymptotes also got shifted 2 units to the left and 3 units up. So that means that the vertical asymptote now is going to go through x equals to negative 2. In other words, that's the equation of it. And the horizontal asymptote is going to come up here. And the equation of that is y is equal to 3. All right, so let's get back into blue here for my graph. So what that means is the graph got shifted up also. So that means that the graph is going to look not quite unlike, but similar to this. Okay, so notice that with respect to the asymptotes, it's like playing that game Operation. You're not going to touch the asymptotes. The graph doesn't pass through them. With no exceptions, the graph will not go through a vertical asymptote. There are exceptions where it can pass through the horizontal asymptote, but that's beyond the scope of what we're going to work with today. Okay. All right, so they want us to take a look at the calculator now and see if we actually got this right. In other words, go put it into our calculator. So let's go back to our calculator here. Hit the y equals, clear out any craziness you happen to have in there. And we need to put in that function that we just had, which was what? Well, it's 1 divided by, let's see, what was it again? It's x plus 2 went into the denominator, so that's going to be parentheses x plus 2. Do not forget your parentheses. And then plus 3. And if we do a zoom 6 or do a zoom and a standard, we see, sure enough, it got shifted 2 units to the left and 3 units up. All right, now next thing that they want us to do here is they want us to write this as a single function. So if we're going to write this as a single function, then that means that what? Well, let's see, g of x was equal to 1 over x plus 2. I went kind of fast with that on the calculator. Probably should have done it here first. Sorry about that. But why do I know that? Well, because wherever I found an x in f, I replace that with an x plus 2, and then I'm going to add in the plus 3. Okay, now they want that written as a single function. So I'm going to write that as 1 over x plus 2 plus 3 times x plus 2 over x plus 2. In other words, I took 3 and I multiplied it by 1 in the form of x plus 2 over x plus 2. And that gives me 1 over x plus 2 is equal to, not equal, silly me, plus 3x plus 6, and the denominator is x plus 2. And so now that I have a common denominator, I can rewrite that as 3x plus 7 all over x plus 2. Okay, so that's what it looks like as a single function. Okay, what's next? I don't know, what is next? Okay, so let's get over here. I'm going back to the slides. Let's look at 1 over x squared. Okay, so if we're looking at 1 over x squared, again, this is one of our toolkit functions. And we see, again, the domain and the range here. They're slightly different than the previous one. In particular, well, the domain, that stayed the same, but the range is going to get changed, isn't it, right? And so we know that the domain here in this function is the set of x's such that x is not equal to 0. And we see that the range here is what? Well, we can see it from the graph. We can see that what? Y such that y is strictly greater than 0. And again, we have a vertical and a horizontal asymptote going on here. Our vertical asymptote, again, is the y-axis, and our horizontal asymptote is, again, the x-axis, all right? Okay, cool. So what this tells us about the properties of our function here is that as x approaches 0 from the negative side, f of x goes to positive infinity, and as x approaches 0 from the positive side, f of x goes to positive infinity. So no matter which side I come at it from, I'm going to positive infinity. Okay, what else do we see about this? Well, as x goes to positive infinity, we see that f of x is approaching 0. And as x approaches negative infinity, we again see f of x is approaching 0. So no matter which way x goes, blows left or right, we get those positive infinities, okay? Positive or negative infinity, respectively, okay? So one last thing, let's make sure we got this. So we know that the horizontal asymptote is again at y is equal to 0, and the vertical asymptote is at x equals to 0. Okay, so let's blow past that because we just did all of that information. I don't need to do it twice. And let's look at your turn 2π. So 2π says go ahead and use g of x now equal to f of x minus 3 plus 1, where in this case f of x is equal to 1 over x squared. All right, let's get a fresh whiteboard here. So this is your turn. By the way, you are writing these down, right? Because these are your turns, right? I should have been a little better about that in the last one for you, but we'll get it. Okay, so g of x is equal to what again? Let's see, what was g of x equal to? G of x is equal to x minus 3 plus 1, f of x minus 3, where f of x is given this time to be equal to 1 over x squared, okay? All right, let's not skip what I did last time. Let's go ahead and do the algebra part first. So f of x minus 3 is going to be 1 over x minus 3 quantity squared plus 1. And so what we see is that this time the graph was shifted 3 units to the right and 1 unit up. So our stock function 1 over x squared has had that done to it. So let's go ahead and let's change the pencil color here. Let's do a graph. Okay, so let's make my coordinate system first. There's a stunningly beautiful x and y axes. I know they're pretty crappy, but that's all right. And let's see, I'm going to go a little faster this time. I'm not going to put in the stock function first. I'm just going to go for what we know happened here. So we got shifted 3 units to the right. So 1, 2, 3. So there is my vertical asymptote. And then the horizontal asymptote got shifted up by 1. So that's being 1. That means there is my horizontal asymptote. Okay, and now let's go ahead and put in the graph because we're using our asymptotes as a drawing guide. So we know that this is going to look like the volcano function, so it's going to look not quite unlike, but similar to that. And I'll leave it to you to go put that in your calculator and check it out. But be careful to make sure you put it in as 1 divided by parentheses x minus 3 quantity squared, close that parentheses, plus 1. Okay? So in other words, that's what your y1 would be equal to. All right, now they want us to do a little bit of algebra here, and they want us to get this into a single expression. In other words, they want us to add in that 1. So to do that, well, we know g of x is equal to 1 over x minus 3 quantity squared, but now that plus 1, I'm going to rewrite that as x minus 3 quantity squared over x minus 3 quantity squared, which gets me 1 plus x minus 3 quantity squared over x minus 3 quantity squared. Now you've fulfilled their requirement, got it all written as a single expression, but they're going to want you to multiply out that numerator and denominator. So let's do that. So recall that x minus 3 quantity squared is equal to x minus 3 times x minus 3, which is equal to x squared minus 6x plus 9. So that means this is going to be 1 plus x squared minus 6x plus 9 over x squared minus 6x plus 9, which gets me x squared minus 6x plus 10 over x squared minus 6x plus 9. Okay, don't forget to check this on your calculator. Make sure the graph came out correct. All right, so now what? What do they want from us now? Well, let's see. Oh, they want us to know what the definition of a rational function is. So let's solidify our definition a bit here. Very important definition from the standpoint of what the heck is going on, right? Okay, so this is, getting my pencil back turned, I shut my pencil off. Dang it. So this is the numerator's polynomial and this is the denominator's polynomial. And the big thing that you need to realize is that the numerator and denominator are both polynomials. So our numerator is a polynomial and our denominator is polynomials. And so the stuff we learned in the last couple sections about polynomials is going to be very helpful for what we're going to do in here. Okay, so take a moment and review in your reference book. Make sure you have the definition of a polynomial in there. If not, make sure you go back and find that in the book and get it in there. We'll call that as sharing it with the folks around you, as going and checking your reference book. So the main thing is that a rational function is the ratio of two polynomials. We typically will call the numerator polynomial P and the denominator polynomial Q, for Paul and Quincy respectively. Okay, so given a rational function as part of the investigation of its behavior, both long-term and short-term, we're going to be interested in finding the vertical and horizontal asymptotes. But also, just as before when we work with earlier functions, we're going to want to find out where does it cross the x and the y axis, in other words, our vertical and horizontal intercepts. Well, let's start off with finding vertical asymptotes. So what you may have noticed is that in the previous couple examples, that the vertical asymptotes occurred when we had division by 0. So if we find where the denominator is equal to 0, we will find the equation of the vertical asymptote. Now there is an exception to that, and we'll talk about that in a few minutes. But if you want to find the vertical asymptote, you simply need to find out where is the denominator undefined. Where is it equal to 0? So let's do that. Let's go ahead and do your turn here. Find the vertical asymptotes of the following function g of x. Well, what that says is you just got to take this denominator here and find out where is that denominator equal to 0, and that's going to give you the equations of the vertical asymptotes. So let's take 3x squared minus 14x plus 15, and let's put that into factored form. And if we do that, we're going to get 3x and an x, and then looking like, let's see, they're both going to be minuses because we got a plus on the 15, and that's going to be a 3, and that's going to be a 5. 5x, negative 5x minus 9x gives me negative 14x. So yep, that is the factorization of it. Okay, now before I go on to finding the vertical asymptotes, let's take a quick stop and talk about domain here. So if I was going to do the domain, it's going to be the set of x's such that, well, I can't have either of these be equal to 0. So that would say 3x minus 5 is not equal to 0, or what? 3x is not equal to 5, or x is not equal to 5/3. Okay, so x not equal to 5/3 is one of my restrictions for my domain. And then the second one, hopefully that one's a little bit more obvious, I don't need to do it for you, x cannot be equal to 3. Now those are the way I would define my domain. But when I want to find the equation of the vertical asymptotes, then I'm going to change those domain restrictions into equations. So there's a vertical asymptote at x equals to 5/3. In other words, that's the equation of the vertical line for the first vertical asymptote, and x equals to 3 is the equation of the vertical line for the second vertical asymptote. So notice that finding the domain restrictions is really part and parcel to finding the vertical asymptotes also, with that exception that we talked about that we'll get to in just a moment. Okay, so let's do a quick look at the graph of that. So let's go back to our calculator, clear out the y equals. Let's put that function in there. So we get 2x squared plus 7x minus 15 in the numerator. Oh, my bad, I forgot to open my parentheses. That would have blown things up badly. Got to get an open parentheses in there first. So let's start over. There we go, 2x squared plus 7x minus 15, close the parentheses, put in the division, open the new set of parentheses, and put in 3x squared minus 14x plus 15, and then let's close that parentheses. And then let's look at the graph. Let's go ahead and do a zoom and a standard. You gotta make that sound a little graph, okay? Ah, there's part of the graph. And no, that is not the graph. That is Mike making a mistake on the input here. So let's go back. What did I forget? 2x squared plus 7x minus 15, and then 3 divided by 3x squared minus 14x plus 15. Oh, I got a square there. So where the heck did that come from? Let's get rid of that. Oh, my Lord. There we go. I had some leftover chunks from my previous one here. Going to get rid of all that excess. Always start off with a clear. I'm just showing you, demonstrating, you always should start off with a clear before you start typing into there. You shouldn't just trust it to do it for you. Okay, so now that I got that input correctly, it's looking more like the graph I was expecting. Okay, so notice we have two vertical asymptotes. We want to have one here at 5/3. We have another one here at 3. Kind of a cool, groovy looking graph. We'll talk more about the behavior of those graphs in a bit. The main thing right now, we want to see the vertical asymptotes. Okay. Okay, so what is the exception? The exception is where you have both the numerator and denominator equal to 0 at the same input. That is, there's a common factor between the numerator and denominator. If we have that case, we get a hole in the graph. So let's take a look at problem number 12, which is an example of that, okay? So find the vertical asymptotes for the following. So here's the deal. When you're going to find vertical asymptotes, what you really need to do is not factor just the denominator, but you also need to factor the numerator. You need to start off there. So in every case, when you're looking for vertical asymptotes, your opening move is going to be to factor the numerator and the denominator. That's your opening move. Do that every time. You're not just the denominator. You got to do both of them, okay? So if I factor the numerator here, I'm going to get x minus 3 times x plus 2. And recognizing that as a difference of 2 squares in the denominator, I'm going to get x minus 2 times x plus 2. All right, now, before we go any further, let's do the domain of this function based upon that. So we do the domain of this function here. We see the domain is the set of x's such that x is not equal to 2 and x is not equal to negative 2. Those two values will cause division by 0. All right, now that I've got that, and only after I've got that, I'm going to come in here and I'm going to simplify. I'm going to cancel off the common factors between the numerator and denominator. So I see that one and that one both cancel to become a 1. And the simplified version of my function now is going to be equal to x minus 3 over x minus 2. And so this is the function that I use to find the vertical asymptotes. So the domain is from the unsimplified function. So don't simplify first. Okay, that's how you find the domain. But the vertical asymptotes, those come from the simplified or reduced version of it. Why? Well, because now notice that there's only one, I want to put a squiggle in here. There's only one vertical asymptote. That vertical asymptote is at x equals to 2. And you say, okay, cool, but what was going on? You said that x cannot be equal to negative 2. Well, yeah, we also have to include that, and that's referred to as a hole in the graph. So there is a hole at x equals to negative 2. All right, let's go take a look at our calculator Desmos and see what that looks like on our calculator. So go into our y equals, clear out what's in y1. Don't make that same mistake of typing over like I did last time. Just clear it out of there. And we're going to put in x squared minus x minus 6, close the parentheses, divide, open the parentheses, x squared minus 4. Okay. Do a zoom and a standard here. Hit zoom and hit the option 4. It's not standard, excuse me, zoom decimal. Hit a zoom and a 4 for zoom decimal. And if you see the graph, oh, looky there. Do you see what's happening at the graph right here? At negative 2, there's an undefined point. And so what happens is the graph gets a hole in it. We see our vertical asymptote, though, here is at what? At x equals to 2, just as we predicted. Okay, so that's a little more chewy of a topic than just a vertical asymptote. Make sure you review that example a couple times so that it makes sense to you. All right, let's scroll right on down here. This is the definition of a hole of the graph. You might want to make sure, again, this is in your reference book. The vertical asymptotes of a rational function occur when the denominator of the function is equal to 0 and the numerator is not 0. A hole might occur in the graph when a rational function input is caused by both the numerator and denominator to be equal to 0. In this case, you need to factor both the numerator and denominator and simplify. In fact, you should do that every time. Remember that. It's the first move when you're looking for vertical asymptotes. And then if you get a common factor that cancels between the numerator and denominator, then that's going to be a hole in the graph. All right, cool beans. So we've talked about vertical asymptotes. Let's talk about horizontal asymptotes. To find a horizontal asymptote, we're going to be interested in the long-term behavior of the function. In other words, what happens as x values get really big. So recall that a polynomial's long-term behavior is mirrored by that of the leading term. In other words, we know what the leading term is, we know what the long-term behavior of the polynomial is going to be. Well, likewise, with the rational, the function's long-run behavior can be mirrored, or is going to mirror by the ratio of the leading terms of the numerator and the denominator function. So let me just give you an example of what that means. So if we take f of x is equal to 2x squared minus 5x plus 1, divided by 3x squared minus 11x plus 2, we know that the numerator is a parabola and that its long-term behavior is going to be determined by the 2x squared. In other words, that's going to eventually tell you what it looks like. Similarly, same song, second verse, the denominator is also a parabola and its long-term behavior is determined by 3x squared. So for the rational function, if we look at y equals 2x squared over 3x squared, that's going to determine the long-term behavior of f of x. In other words, that's going to tell us what the horizontal asymptote is. Because when we're talking about long-term behavior with rational functions, we're trying to determine what the horizontal asymptote is, and if it exists. It may not exist. There's many cases where there is no horizontal asymptote for a rational function. Okay, so the way to do this is to break it down into three cases. The first case is where the degree of the denominator is greater than the degree of the numerator, then the degree of the denominator is less than the degree of the numerator, and then when the degrees are equal to each other. So let's take a look at an example of each one of these that try and make sense. Okay, so let's say we give you f of x is equal to, well, let's say it's just 3x over x squared minus 5x plus 1. Well, in this case, the degree of the numerator is equal to 1, and the degree of the denominator is equal to 2. So we've got the case where 2 is greater than 1. So in that case, y equals to 0 is the horizontal asymptote. Now, why is that? Well, here, let's take a look at it. Let's again just take the leading terms. Y is equal to 3x over x squared. If we simplify that, that's going to be equal to 3 over x. Okay, well that looks like one of our toolkit functions, and we know that it's got a horizontal asymptote at y equals to 0. So if that's the case, if when we simplify it, it ends up looking like a over x to the n, then you know that you're going to get y equals to 0 as a horizontal asymptote. This is really good stuff to have in your reference book. You want to have this at the tip of your fingers. Okay, what about if the degree of the denominator is less than the degree of the numerator? So let's make a new function, a new example here. Let's say f of x is equal to x squared minus 5x plus 1, and the denominator is equal to 3x. Well, in this case, we know now the degree of the numerator is 2 and the degree of the denominator is 1. So that's the case where the denominator's degree is less than the numerator's degree, right? So if we again form the ratio of like terms, leading terms between the numerator and denominator, we get x squared over 3x, which will simplify to just x over 3. And in this case, what that is, that's just the equation of a line. So there's going to be no horizontal asymptote, or no HA, okay? All right, one last case here. What if the degrees are equal to each other? So that was the one we had on the previous page. What if I gave you f of x was equal to, say, 2x squared plus 5x plus 1 divided by 3x squared minus 11x plus 2? Well, in this case, the ratio of the leading terms is going to be what? 2x squared over 3x squared. And so if I simplify that, I get back what? Y is equal to 2/3, don't I? And so when you simplify that, that's going to give you the equation of the horizontal asymptote. In other words, it's the ratio of the numerical coefficients on the leading terms. But go through that push-up. Take the time to write down the two leading terms and then simplify it, and you'll see it'll pop out. It'll just give you the equation of the horizontal asymptote. Okay, so this is all written up again in the blue box in the textbook. You need to make sure you get that into your reference book. I'm going to let you do that on your own. And let's go find the horizontal asymptotes for the following function. Okay, well, how are we supposed to do that? Well, we just need to come in here and say, okay, so y is equal to 2x squared over 3x squared. In other words, I just look at the leading terms. I make sure that my polynomials are in descending order, grab the two leading terms. This simplifies to 2/3, so I know that the horizontal asymptote is given by y is equal to 2/3. Now I'm going to have, in the interest of time, I'm going to let you go ahead and either use your calculator in Desmos and see that indeed this does have a horizontal asymptote at y equals to 2/3, okay? Let's find the horizontal asymptote of the following function here. So again, we're going to go what? Find the leading terms. Y equals x squared over x squared, and we see that that gives me back what? Y is equal to 1. So the equation of the horizontal asymptote is at y equals to 1. Again, you get out your calculator or Desmos for me and graph that and make sure that you see that the horizontal asymptote is at equal to 1, all right? Okay, I'm going to go ahead and take a pause here. This is good enough to finish the first part of this video. We'll do a second part and we'll come back and talk about intercepts.